So I imagine a lot of you guys know that vaccines often require multiple doses to be effective. And these doses are usually given at a healthcare facility of some kind by trained personnel, requiring multiple visits to complete a vaccine series. Well, what if you could give a single shot of the vaccine, and that shot contained all the components necessary for the first and subsequent doses? And wouldn't that be especially great for places on Earth that are remote and have scarce access for resources to administer vaccines in the first place? Well, Anna Clinic and Bob Langer's group have been working on such technology for several years, and my image is a slice of that technology. So let me tell you how it works. To make a single injection, self-boosting vaccine, they use micromolded core shell particles. These particles are hundreds of microns in size and are made of a biodegradable, biocompatible polymer shell on the outside containing a core that's filled with vaccine. The shell is made of two parts, a base and a cap. The base holds the core that's filled and the cap is sealed on top. On the image on the left, below the red and the blue, you can see one of these particles finished, ready to go into the body. In a wet environment, you can see on the next image that the cap degrades and deforms first. The base will degrade later. And on the right, you can see a micro CT image, an X-ray slice of what one of these particles looks like. And you can see pores that are forming in the cap. And it's through these pores that the contents of the particle will escape in a burst. And that burst is timed to occur at a specific time point after administration of the particle. Now you can develop several populations of these particles so that each population breaks down and releases its contents at a different time point. That's what the red, green, and blue cubes represent on the graph. If you mix these together and inject them into an individual, they'll break down at different time points, and you'll get vaccine doses released in pulses, and these pulses can be timed to a vaccine administration schedule. Now, whenever you inject anything into the body senses that and mounts a foreign body response. This is coordinated by proteins binding to the surface of the object, immune cells coming in, like neutrophils, monocytes, and macrophages, and finally fibroblasts coming in to wall off the object. The question was asked, what does the foreign body response look like for these particles, and does it affect cargo release? And my image was from one of the first experiments that was done to answer these questions. Let me tell you about that experiment. Empty core shell particles were injected under the skin of mice, biopsied, frozen, and sliced like you would slice a slice of bread. I then used a dye to highlight immune cells that were part of the foreign body response, monocytes and macrophages, and then took photographs using a confocal microscope. I compiled those photographs into the image as well as the 3D rendering of the slice of the particle. In red, you can see the walls and the base of the particle. In blue, the biodegrading cap. And in green, you can see the immune cells that made it inside the particle at this time point. Now, normally, you would see immune cells on the outside as well. But when I was doing the dyeing procedure, the slice fell out of the skin section, and I took the photograph anyway. But if you look really closely on the top left-hand side here, you can see that there are a couple of little straggler cells that hung on for dear life and still made it into the photo. Going forward, understanding how the body interacts with these particles will ensure that they're able to deliver their cargo most effectively to folks around the world who need access to this type of technology. And it bears saying that you can not only deliver vaccines using this technology, but also things like drugs and chemotherapy. I'd like to thank PI's Anna Clinic and Bob Langer, Morteza and Maria for their help with the experiments, John for his advice, Charlene and Kathy in the Histology Core, and Jeff Wyckoff in the Microscopy Core, as well as funders. Thank you.